All right, in this video, we are going to take a look at section 6.5. So in this textbook, the author splits up the conversation of logarithms into two pieces, two sections. 6.4, he introduces you to logarithms, and he defines the logarithm as the inverse of the exponential. Talks about how to evaluate logarithms, convert between logarithmic form and exponential form, and even discusses graphing, tying the graphs back to the idea of the inverse of the exponential. In this section, he builds upon that conversation and finishes off the last couple pieces, which would be really the properties of logarithms. So let's take a look at this section together here. So first of all, I want to point out to you here, there's a couple different groups of properties of logarithms, right? And the first one I want to point out to you is ones that I think are obvious, but this book and most algebra books list them as special properties. So for example, if we look at letter A says show that log base A of 1 equals 0. And this is actually going to be our first property of logarithms. But let's point out to ourselves, like if we were going to justify that this is true, what we would do is what we did in the prior section in 6.4. We could rewrite this in an exponential form. So think if I'm going to rewrite this in an exponential form, what that would look like. I would have the base A raised to the power of 0 equals 1. Right? And if I use that definition and I rewrite it as a to the power of 0 equals 1, then I know this is true, right? I know from properties of exponents that anything to the 0 power equals 1. So therefore, this is a legitimate statement in logarithmic form. Oops. All right, so this will be our first property of logarithms. Now the second property of logarithms we're going to be given is that log base A of A equals 1. Right? And again, if I use this definition we gave back in the last section and I rewrite this in an exponential form, it's the base of A to the power of 1 equals what's inside, right? Equals the A inside the logarithm. So A to the power of 1 equals A, and we know that that's true, right? 3 to the power of 1 equals 3. And this is true for any base A. So these are our first two properties of logarithms. Right? The log of 1 will equal 0. So no matter what the base of the logarithm is, the log of 1 will always equal 0. So what this is going to connect back to, right, is the x-intercept of the graph. If you think about the graph of a logarithm, let me take out my pen real quick. When we graphed logarithms, we had a vertical asymptote right here on the y-axis, and then we always had an x-intercept of 1. And the graph looked something like this, right? So there's my x-intercept of 1, right? Log of 1 equals 0. And that was always fixed on the graph, okay? And then, the other property is that the log base A of A equals 1. So if the base of the log matches the number inside, I'm going to get 1, right? So log base 5 of 5 would equal 1. Log base 10 of 10 would equal 1. So those are the first two properties of logarithms that we see in this section. All right, now let's take a look at the next. Couple properties that we're going to see in this section. So first, what I want to do is remind you that I'm trying to remind this of you a lot, right? Is that the base A logarithm and the base A exponential are inverses. Now, if we think back to the inverse section in 6.2, what we talked about was that if we compose the two functions, they undo each other, right? That was the whole idea of inverses. So if I do the composition of the two functions, they will undo each other, and I'll just get x out as my result, right? If I do the composition of the two functions, I get just x in return, right? So let's do the composition in this particular direction. All right, so if we do the composition in this direction, then what we're going to get is f evaluated at log base A of x. And if we continue with the composition, that's what it looks like. Right? So if I do f composed with f inverse, I'm going to get a to the power of log base A of x. So all of this is in the exponent when I do the composition. And I know because these are inverses, they undo each other. So this is going to be the next property of logarithms right here, is that a to the power of log base A of x will just be x. Those are going to cancel each other out. And the book writes it this way, right? They say a to the power of log base a of m would equal m, right? So the base a exponential, base a logarithms cancel each other out when I compose them in that fashion. Now, if I compose in the other direction, what does that look like? So if I compose in the other direction, what that looks like is log base a of a to the x. And again, because those are inverses, I know they're going to cancel out, and I'm going to get just x drop out of that result. Again, the book uses different letters, right? But this is log base a of a to the r, and that will equal r. Right? And again, these are inverses. They're going to wipe each other out, and I'm going to just get the input out of that expression. So this would be the next two properties of logarithms that you would see in the textbook. So let's look at a couple illustrations of that idea. Here's letter A illustrating the first property here. So I have 2 all raised to the power of log base 2 of pi. So because these are inverses, that's this composition, and that's going to all just equal pi. Now, letter B is illustrating the second property here. So this is saying I have log base 0.2 of 0.2 to the power of negative root 2. Now, because the base of the log and the base of the exponential match each other, like we see in this property, then they're going to literally cancel each other out. They're inverses, and I'm going to get just the exponent, negative root 2, out of that result. All right, so pause the video for a second, and you try letter C. All right, what did you get? All right, well, hopefully what you did was you used the second property here, right? So we see that ln, remember, is log base e, and then this is base e exponential. So what I really have here is a log base e of e to a power. So these are going to wipe each other out, and I'm going to get just the exponent of kt. All right, now the next 3 properties of logarithms are really properties of exponents, okay? So these look kind of ugly, they look kind of scary, but just to point out to you, they really are properties of exponents. So remember, when I multiply like bases, I add exponents. That's really what property number 3 is. Property number 3 is multiplying like bases, adding exponents, just written in a logarithmic form. So what this will allow me to do is take the log of a product and break it up as the sum of 2 individual logs. This is sometimes called the product rule. This book calls it the log of a product equals the sum of logs rule. That's kind of a mouthful, and this is sometimes called the product rule. Now, the next property is sometimes called the quotient rule, because it says that the log of a quotient equals the difference of the 2 logs. All right, now what this is, remember, when you divide like bases, you subtract exponents, and that's what this is in logarithmic form. And then the next property, the final property we'll see here, is basically when I have a power raised to a power, I multiply the exponents, and that's what this is written in logarithmic form. So this basically says, well, here's how I'm going to use it. Log base a of something to a power, I'm going to be able to take that power and pull it in front of the log as a coefficient. So you can see the r is gone here, and I've pulled it in front as a coefficient. So let's take a look at a couple examples where we apply these properties. So the first one, what we're going to do, let's take a logarithmic expression and let's split it up, right? So notice we have a single logarithm here. We're going to split this up. Notice the directions say we're writing a logarithm as a sum of logarithms. And what that really means is it might be a sum, it might be a subtraction, right? I'm going to, in essence, be taking these properties and going in this direction. I'm going to have a single log, I'm going to split it into a sum, or a single log, I'm going to split it into a difference. Right? If I have a logarithm with an exponent, I'm going to pull the exponent in front as a coefficient. So that's going to be our goal in this first example here. So first, let me remind you, when I have something that is under a root, I can really write that as an exponent. So I can really write this as x minus 1 raised to the 1/3 power. Right? So remember, we had simplified square roots and we wrote them as 1/2 powers. We can write cube roots as 1/3 power. So we're going to do that. Right? So this first step, I'm going to write that as a cube root, and then I'm going to split this product up. So I have x squared times the cube root, and I'm going to split that up as a product. Right? So I'm going to write that as a product, into a sum form, right? So I'm writing it into a sum form, and then I'm taking the cube root and writing it as a 1/3 power. So kind of did two things at once there, right? Wrote the cube root as a 1/3 power, and then I'm taking the product rule and splitting it into a sum. Now the only last thing I could really do here is take this exponent and pull it in front as a coefficient, and take this exponent and pull it in front as a coefficient with that third property that we had on that prior slide. So I'm going to take the coefficient, I'm going to take the exponent and pull it in front as a coefficient. And that's called the power rule. So I take the 2, pull it in front, take the 1/3, pull it in front, and then I'm done. That's as far as I can go. Right? And the reason that I know I can't go any further inside this logarithm is no more products or quotients or exponents. And same here, no more products, quotients, or exponents. So I've simplified as far as I can. All right, let's do another example here. So here I have log base 6 of all of this stuff, right? So again, I'm trying to split this up. So the main thing I see happening here is a division sign. So I have log of a quotient. So I'm going to use that property, or the log of a quotient is the difference of the logs. And I'm going to split up that logarithm into a difference of logs. So the log of the numerator minus the log of the denominator. Right, and then I'm similar to the last example. I'm going to take this coefficient, this exponent, I keep saying it backwards, taking this exponent, pulling it in front as a coefficient. I'm going to take this exponent, pull it in front as a coefficient using, the power rule, and that's going to be my final form here. So I can't really simplify this any further. Now, let me tell you, some students will have a question and say, well, wait a second, here's an exponent. Why can't I pull this out front? And I want to point out to you, this exponent is only on the x term. It's not on the entire expression, x plus 3. Right? The exponent has to be on the entire expression. See how this exponent was on the entire expression? I can pull it out front. That's what this says to me. But if the exponent's only on one of the terms, I can't pull it out front. So I'm done at this point. I can't simplify this any further. All right, let's look at a couple examples where we'll go backwards. So we'll use the properties in the reverse direction. Right? So in other words, we're going to be given a expression like a sum of logs, and we're going to combine them into one logarithm. Right? So we're saying write the expression as a single logarithm. Now, here's a kind of rule of thumb. Rule of thumb here is we're going to go backwards of what we saw in those first two examples. So anything that's a coefficient, like the 3 that I have here, I'm going to have to pull that inside as an exponent first. So I'm typically going to deal with coefficients first. I'm going to kind of work backwards like we did those first two examples. So first thing I'm going to do is pull that in backwards. So I'm going to take that 3, pull it in as an exponent. All right, so now that all of the coefficients are pulled inside, and our powers, now I'm going to use the sum rule and write this as a product, right? So I'm going to use that rule, and I'm going to go backwards on this formula, right? So I'm going to take the sum, I'm going to write one single logarithm, and it's the product of the insides of each of those logs. So I'm going to take the inside of this log, and I'm going to multiply inside one single logarithm. And there's my combination, right? I've simplified this expression into a single logarithm. And nothing I can really do with that in terms of combining. I've combined everything into one logarithm. We're done at that point. Let's do one more example here. So let's suppose we want to write this as a single logarithm. So again, first step, take this coefficient, write it as an exponent on the 4. Take this coefficient of 2, write it as an exponent on the 5. It's going to be my first step using that power rule. Now, because I have numbers in here, notice this is really the square root of 4, so that's going to be 2, and this is really 5 squared, which is 25. Right? So I'm going to go ahead and kind of simplify those. Right? And then I have a subtraction. So what I'm going to do is use that rule, right, where I have the subtraction, and I can pull them in as a coefficient, a quotient, right? So I call this the quotient rule, right? So we're going to use it backwards. We have a subtraction, and we're going to pull everything in as a quotient. So I'm going to pull everything in as a quotient. So I'm going to have this is the numerator, this is the denominator. And then I'm really done at that point. I can't simplify this any further. I've combined everything into one single logarithm. All right, so last example here where we kind of combined everything. So I notice I have an addition. So we're going to end up doing a product. And notice I have a subtraction, so we're going to end up doing a quotient. Before we do either of those, we have to pull the coefficient in as an exponent. Right? So I have the 2 here. I'm going to pull it in. This will be 3 squared. And then I have the 3 here. I'm going to pull this in. This will be 2 cubed. Right? So that's the first thing we have to do, is write those. So this will be 9. This will be 2 cubed, which is 8. So I'm always going to work left to right. Remember, our orders of operations are PEMDAS, right? PEMDAS, parentheses exponents first. M and D is multiplication, division next, and then the last addition, subtraction. So because all I have left is addition and subtractions of terms, I always move left to right. So I'm going to grab these 2 guys right here first, and I'm going to look at the addition of these 2. I'm going to combine that into one single logarithm. So I have the log of the 9 times the 8. So I get the log of 72 here. So these 2 combine into this one single log, and then I have the subtraction left over. So then I'll use the quotient rule, and I'll write that as a division. And then so I'm done. I have one single logarithm that I've done here. Now, let me point out to you guys, what we're doing here with these 3 properties is not really very exciting yet. But when we get to the next section, we're going to start to use these quite extensively. So we're going to look at some word problems. Remember, the beauty of math is in applications. We're going to ultimately look at some word problems, some applications that involve exponential and logarithmic functions. We're going to have to solve equations that are exponential, solve equations that are logarithmic, and sometimes we need to simplify the logarithm. So we might have an equation, like let's say all of this stuff was set equal to 0, right? Much easier to combine all of this stuff into one logarithm and set that equal to 0. So that's really how we're going to use these properties in the next section. We're going to use them like we saw in these last couple examples. We're going to combine logarithms into one single logarithm. That's going to be the most efficient way for us to solve equations. All right, now the next set of properties given in this section, again, I think are kind of obvious, but whenever you're talking about something new, like a logarithm, a lot of times for a student in an algebra class like this, I remember the first time I took this algebra class, these looked really scary, right? I mean, the first time you see logarithms, they're weird, and you really haven't seen them before this class. But I think if you think about like a function you are comfortable with, this property will make sense. So let's read the property first. It says that if m equals n, then a log base a of m will equal log base a of n. So basically this first line is kind of saying that you can log both sides of an equation, right? So if I have like, x equals 5, I can log both sides of the equation. If for some reason that was convenient, this is saying you can log both sides, right? And then the other direction here is basically saying if you have log base a of a number and log base a of a number, then we can literally like drop the logs on both sides, and the numbers on the inside have to equal each other. Now think about the square root function, right? If I know that like m equals n, I can square root both sides of this equation, and there's still equality that's held there. So this first line is kind of the same thing, right? It's kind of saying that if I have two things equal, I can square root both sides. And then the second line is kind of saying the backwards, right? It's kind of saying like if square root of m equals square root of n, then the things under the roots must be the same. If the square roots are equal to each other, then the things under the root must equal each other. So I don't want you to see this property as something, all crazy and mystical, right? It's really the same thing you've seen with square roots in the past, right? We won't use these properties all that regularly, but there will be some times that we use them. So I like to show that in this PowerPoint, right? This lecture video, because there will be some times we use these properties, and in particular to be the first one where we'll log both sides of an equation, just like we might square root both sides of an equation. All right, so finally the last property we're going to look at is what we call the change of base formula. Now, before we write the change of base formula, I want to do a little bit of exploration. So let's suppose we are being asked to find the value of log base 3 of 12. Now, the way that we did this in the last section was we basically said, well, what does log base 3 of 12 equal? And then we wrote that as an exponential. You know, we basically said, you know, this is saying 3 to what power would equal 12. Right? Now, this isn't an easy question to answer, right? Because we know that 3 squared is 9. We know that 3 cubed is 27. So this exponent has to be somewhere between the square and the cube. 3 to the 2 and 3 to the 3. Right? We know 3 squared is 9, 3 cubed is 27. So somewhere in between, right? This might be like 2.4 or 2.3. Not sure what it is. Okay? So we could explore. We could take out our calculator and we could start guessing numbers. We could say, oh, 3 to the 2.5 is 15, so that's too big. So maybe it's 2.4. We do 3 to the 2.4, and that's a little too big. That's not 12. That's almost 14. So we got to get even smaller. Maybe it's 3 to the 2.3. So we see 3 to the 2.3 is pretty close to 12. So maybe it's 2.2. So we do 3 to the 2.2 and we're below 12. So we're somewhere between these two numbers, 2.2 and 2.3. Somewhere between those two is our solution. So maybe we pick right in the middle. What's between 2.2 and 2.3? 2.25. So if we pick 2.25, we get a little closer to 12. Right? Now, obviously, this is crazy. I don't want to have to, evaluate a logarithm by guessing and getting closer and closer. So this last property that we look at is called the change of base formula, and it gives me a tool to be able to evaluate a logarithm very quickly. Right? So here's the change of base formula. Basically says that if I have a base A logarithm, I can change it to any other base that I want. Base B, notice base B here, right? So I take the inside of the original logarithm, that's the inside of the log in the numerator, and I take the base of the original logarithm, and that's the inside of the log in the denominator. Now, keep in mind, let me pull up my calculator or whatever you might be using, right? On my calculator, all I have is log base E and log base 10. So if I'm doing a change of base formula, I am, I'm changing to base 10 or base E. Right? And if you look at your smartphone, right? Let's say you're using a calculator on your smartphone. I know the iPhone. If you turn the iPhone on its side, the calculator changes into a pretty deep scientific calculator, and it has logarithms on it. It has log base 10 and log base C, and I know Android phones have the same. You can download free calculator apps on your phone, where they're full scientific calculators as well. You could even Google search web-based scientific calculator, and you'll find some free ones out there. All right. So again, if you haven't bought the TI, don't go buy it at this point. The semester's almost over. So if we're going to change the base, we're going to change the base 10 or base E here. Right. So just to show you in the slides, what I said was we're going to change the base 10. Right. So let's suppose I have log base 3 of 12. I'm going to change to base 10. So here's log base 10 of 12, and here's log base 10 of 3. So that's what this is illustrating for me. I'm changing the base of 3 to a base of 10. That's what I did over there. And then the inside goes to the numerator. The base goes to the denominator, right? So log base 3 is 12, gets log 12 over log 3. All right, now if I take out my calculator and I evaluate this, so I got my calculator on, so I'm going to hit log, and then punch 12, and let me close the paren, and then I'm going to divide by, and then I'm going to punch log and hit 3 and close that. And when I hit enter, I'm going to see we get about 2.25-ish, close to what we got. So apparently 2.26 was a better approximation, right? So I would be able to say 3 raised to the power of 2.26, and I should be even closer to 12. That's pretty darn close to 12. Now keep in mind, with any of this stuff that we do here with these approximations, right? This approximation that I have here, 2.26, right? Keep in mind that the more decimal accuracy I keep, the better my approximation. So if I say that log base 3 of 12 is equal to 2.26, that's an approximation, right? I want more decimal accuracy is a better approximation. All right, let's look at a couple more real quick examples. So I just put the log change of base formula up here, right? And again, pointing out to you, we're either going to change to base 10 or they're either going to change to base E, right? We're not really going to pick any other base. So let's say we wanted to evaluate log base 5 of 89. So again, I could choose base 10 or I could choose base E. I can choose log base 10 or log base E. Both are going to give me the same answer. So in this example, what I picked was log base E. So if I do ln of 89 divided by ln of 5 and I plug that in my calculator, I'm going to get about 2.7889. Right? And again, the more decimal accuracy I keep, the better my approximation. Right? In this case, I kept 4 decimal places. So 5 raised to the power of 2.7889 is going to give me about 89. Okay? It's going to get me pretty close. So in this next example, suppose I have log base root 2 of square root of 5. This printing comes out weird. Keep in mind this is the base of the logarithm, all right? This is a subscript. Now over here I used ln. On this example, I'm going to use log base 10 just to show you that I get the same result. So here I'm doing log base 10 of the original inside, and then I'm going to divide by log base 10 of the original base. So if I plug that in my calculator, I'm going to get about 2.3219. And again, I could easily check that. I could say square root of 2 raised to this power would equal that number. All right, now I want to show you one more cool thing about the change of base formula that we'll see really soon. And you're not going to see this in your homework, right? I just want to show this to you real quick. So in the next section, we're going to solve equations. And we're going to solve an equation like 2 to the x equals 9. And basically what we're going to do to solve this equation, we're going to rewrite it in a logarithmic form, right? Now, when we get the solution, log base 2 of 9, it would be really convenient to get a decimal for that. So we would take out a calculator, we would do the change of base, and we would get a decimal for that. And then we could check our answer, right? We could say 3.170, plug it in here, and I should be able to check my answer. So we'll use that change of base formula in the next section when we solve equations. Now another cool thing you could do with the change of base formula was back in the prior section, 6.4, we graphed logarithms. Now again, if I'm using my graphing calculator, all I have is base 10 and base E. So if I was graphing an equation like log base 3, I wasn't able to graph that on my calculator. Now Desmos, you could graph that really easily, but on my graphing calculator, I couldn't. So if I was going to check my work in the prior section with my graphing calculator, I'd have to use the change of base formula. So I could change it to ln of x over ln of 3, and I could plug that into my calculator, and it would be the graph of log base 3 of x. So 2 kind of cool ways in which I can use that change of base formula that we'll see in the next section, or we could have used in the prior section. All right, so that's everything we talk about in this section. Again, a quick summary here. We talked about properties of logarithms. We had quite a few properties of logarithms that we wrote down. We did some examples to illustrate those. As always, if you have questions on anything that you're working on in the homework or anything from the lecture videos, please post on the discussion board, and I will see you guys in the next video.